Professor Ganzburg from Hampton University with talk discretization theorems for entire functions of exponential type. Please, continue the stated news.
Okay, so there are several important events in July in Europe. Wimbledon, Euro 24, and this, of course, workshop. So I'm grateful to the organizers for inviting me to here. By the way, I didn't attend any of the first two events, so it's great to be here. Okay, so I would like to talk about discretization of entire functions of exponential type on the m-dimensional Euclidean space and m-dimensional cube. I will use the regular LQ space on a measurable set S, where Q is between 1 and infinity, including 1 and infinity. Okay, the regular norm is given here. What do you mean by discretization theorem? Actually, I like entire functions of exponential type, but discretization of them, it's my first attempt. That is why I need to explain what I mean by discretization theorem. Let B be a vector space of measurable functions on a measurable set S. Let Q is between 1 and infinity. And discretization theorem for B, it states that there exists a finite or countable set of knots such that, there exist two constants C1 and C2 such that these inequalities hold. Okay, it's well known. For Q equals to infinity, the right inequality above is trivial with C1 equals to infinity, and the inequality can be written in this form. In this case, basically, the discretization theorem sounds like that. For any positive gamma, there exists a set of knots such that this inequality holds. In this talk, we often refer to these inequalities as LQ discretization theorems and L infinity discretization theorems, respectively. Note also that good estimates of number of elements in the set of knots is needed for each discretization theorem, of course, in case when number is finite, number of knots is finite. So it's for bounded sets. Actually, we present in this talk stronger versions of the inequalities mentioned before. First, we do not just prove the existence of a set of knots such that above inequalities hold. Instead, we prove the corresponding inequalities for wide classes of knots. And second, for the left-hand side of the first inequality and for the second one, we do not assume that function belongs to LQ, and rather prove it. In other words, we assume that this sum, this sum is finite or supremum is finite, and prove that F belongs to LQ. By the way, the proof is kind of long and technical. Discretization theorems is still a hot topic in classic analysis. For example, at this conference we can see a number of outstanding researchers who contributed much to this area. Among them Feng, Boris, Andras, Irina, Alexei, Vladimir, Sergei. I'm not sure about Irina, I think she didn't come yet. Okay. And others, of course. Now, short survey, it's not really very short, but it's survey for sure. Discretization theorems have been initiated in 1930s, 1940s by Bernstein. I pronounce Bernstein because in such way it was pronounced in Russian. In America, often in Germany, Bernstein or Bernstein, okay? Cartwright, Marcinkiewicz, Zygmunt, Duffin, Scheffer, and others. Influenced by problems of metric entropy, numerical integration, and interpolation, this topic has revisited in the 1990s, much to the efforts of Kashin, Tebelekov, Lubinsky, and others. In most publications containing discretization theorems, the space B is one of the following spaces: real or complex valued trigonometric polynomials, algebraic polynomials, entire functions of exponential type. By the way, I will use abbreviation EFET for entire functions of exponential type. And also exponential polynomials. And below I provide a short survey for each of these spaces. The reason that I included in this survey trigonometric, algebraic, and exponential polynomials, not only entire functions of exponential type, is that first, trigonometric and exponential polynomials are special cases of entire functions of exponential type. And second, in some cases, we derive discretization theorems for entire function of exponential type by using the corresponding theorems for algebraic polynomials. Okay, trigonometric polynomials. The story begins, like many others in approximation theory, with Bernstein in 1931, who proved the following L infinity inequalities. I will not discuss them. It's typical L infinity discretization theorems. But it's 1931. The corresponding LQ discretization theorems for univariate trigonometric polynomials were proved by Marcinkiewicz and Marcinkiewicz-Zygmunt in the 1930s. The results were extended to multivariate trigonometric polynomials with their spectra in a parallelepiped. And the problem of proving LQ discretization theorems for multivariate trigonometric polynomials with their spectra in a set A and with optimal estimates for number of elements in the set of nodes is still open in case of more intricate sets A. For instance, in case of hyperbolic cross A, optimal estimates are known only for Q equals to 2, okay, by Temlekov in 2017. Okay, algebraic polynomials. Univariate algebraic polynomials are easy to describe by discretization. L-infinity discretization theorems for univariate algebraic polynomials immediately follow from Bernstein's inequalities I presented above for trigonometric polynomials. By the standard substitution, x equals to b cosine of t. Many discretization theorems have been established for multivariate polynomials. In particular, the following general result was recently proved by Day and Primack. It's 2023. The following theorem. For any gamma, there exists a constant C such that for every n and every convex body, there exists a set of knots with the number of elements in this set less than or equal C times n to the power m, such that the following inequality holds for every multivariate polynomial q of degree n. It's multivariate case, I'd like to remind you. It's typical L infinity discretization theorem, but for multivariate polynomials on any convex set.
What is the degree n for multivariate polynomials? So
Degree.
is it the largest degree in every variable?
No, it's total degree, total. By the way, it doesn't matter actually. The theorem was conjectured by Croy in 2011 and was proved in 2011 for all convex polytopes in certain other domains in Rm. In addition, he proved the conjecture for m equals to 2 in 2019. We will use this result for certain discretization theorems for if it is on a cube. Okay, now entire functions of exponential type. Of course, unlike polynomials, the discretization of entire functions of exponential type obviously requires an infinite set of knots. L infinity discretization theorems for entire functions of exponential type are known since the 1930s. Cartwright, Duffin-Scheffer, Bernstein, Berling, Blank-Ulansky, and others. A number of people worked in this area. Typical result, for example, by Bernstein of 1948 states that if this condition holds, then for every entire function f of exponential type of at most polynomial growth, so not just bounded, the following inequality holds. It's kind of precise result. The celebrated LQ discretization theorem was for entire function f from LQ of exponential type was proved by Polya and Plancherel in 1937. So it's kind of regular inequality, regular LQ discretization theorem, where x nu are so-called sampling sequences. Okay, many other people worked in this area. For example, Berling, important paper of 1989, and others. Logvinenko in 1990 proved the multivariate Cartwright type theorem, replacing the above univariate condition of Bernstein with the condition that x nu is a delta covering net for Rm. Its definition will be given later. His result states that if this condition holds, then for every multivariate entire function f, m in each variable, the following inequality holds. Okay. In 2013, Pesenson discussed LQ discretization theorem of the regular form of this form, and he proved that there exists a set of knots such that for all entire functions f of exponential type with f from LQ, the inequalities above are held. He actually proves a more general result, replacing f of x nu with special compactly supported distribution. In addition, note that in our theorems discussed later, we first drop the condition f from LQ, second, prove the inequalities for a wide classes of omega, third, find a necessary and sufficient condition on omega for the right inequality to be valid, and sufficient inequality, sufficient condition on omega for the left one to hold. Okay, so it's time to finish probably the survey and move, oh no, sorry, still exponential polynomials. Every real multivariate exponential polynomial of this form is an entire function of high exponential type in case when n is large enough. But the discretization is, of course, on a compact set, mostly convex. Crow in 2022 established L-infinity discretization theorems for real valued exponential polynomial with this separation condition. He proved the L-infinity discretization theorems for convex polytopes and convex polyhedral cones with the following estimate that actually this estimate is sharp with respect to n up to the logarithmic term for the univariate exponential polynomials, but for multivariate exponential polynomials this estimate is not sharp, so it's not the case for m greater than 1. Crow also established weighted version of LQ discretization theorem for a real valued exponential polynomials. All right, now survey is over, and to formulate some results we need some notation and definitions, actually regular, nothing new, but it's needed to be mentioned. Rm is the Euclidean m-dimensional space, Cm is the m-dimensional complex space. We also use some cubes with edge lengths 2m, centered at 0, and cubes centered at x. Throughout the talk, V is centrally symmetric with respect to the origin, closed convex body in Rm, and V star is the polar of V. The set V generates the norm on Rm by the following equality. Okay, it's well known. In particular, when V is a cube, then we have the following norm, which is generated by the cube on Rm. Now we need, first of all, definition of entire function of exponential type. We say that an entire function has exponential type V if for any positive epsilon there exists a constant such that for all z from Cm the following inequality holds. There are many definitions of entire function of exponential type. It's one of them. They're basically all of them are equivalent, at least for the entire function of exponential type of polynomial growth on Rm. The set of all entire functions of exponential type V is denoted by BV. Okay, I appreciate your patience. We need 3 more definitions. Okay, these definitions basically are known. They describe the set of knots. Set of knots is infinite, so it's a sequence. We say that a countable set is a delta covering net for Rm if for every x from Rm there exists x nu such that the norm of x minus x nu norm in this cube norm less than delta. Now we replace delta covering net by delta 1 packing net. The definition 3 says that a countable set is a delta 1 packing net for Rm if the difference between any 2 knots, again in this norm, greater than or equal to delta 1. And final definition, we say that a countable set omega is a delta 1n packing net for Rm if there exists 0 or a positive integer n such that any cube with edge length delta 1 and centered at x nu contains no more than n plus 1 points from this omega. In other words, okay, the 3 equivalent definitions are given. The first one, omega is a delta covering net if and only if the family of cubes, like that, family of cubes cover Rm, is delta 1 packing net if and only if the family of open cubes is pairwise disjoint. And finally, omega is delta 1 n packing net for Rm if and only if for every nu from n the open cube with edge delta 1 centered at x nu contains no more than n plus 1 knots from omega. In particular, a delta 1 packing net coincides with delta 1 0 packing net. Okay. Okay, it's obvious mistake here. That means, okay, no, that's correct. Delta 1 0 packing net. Okay. Okay, finally, theorem 1. So it's one-sided LQ discretization theorem where Q between 1 and infinity excluded infinity. If omega is a delta 1 n packing net for Rm, then the following one-sided LQ discretization inequality holds. So delta 1n packing net. Omega is a delta 1n packing net. The second part, this is A part of theorem. Part B of the theorem discusses the necessity condition. It turns out this condition is necessary. So if this inequality holds with a fixed number C1 for every function from BV and a certain set omega, then there exists such delta 1 such that omega is the delta 1 n packing net for Rm. So in other words, the inequality holds if and only if omega is delta n packing net for Rm. It's this one-sided inequality. Theorem 2 deals with opposite one-sided inequality. Let now omega be a delta covering net. Before that, you remember it was delta n covering net. Now it's delta covering net. delta 1 packing net, sorry, for theorem 1. Now it's delta covering net with a small enough delta. If f from BV, note that we don't assume f from LQ. And this sum is finite, then the typical LQ, one-sided LQ discretization inequality holds. What about part B? Part B about necessity. Unfortunately, it's not necessary and sufficient. Some sufficient conditions actually can be proved. If this inequality holds for any fixed C2 with this sum finite, and in addition let omega be delta 1 n packing net for Rm, then there exist delta such that omega is a delta covering net. So we have some additional condition needed to prove the necessity. So it's like weak necessary condition, okay? Weak necessary condition. I don't know, and probably it's not easy to find the a necessary and sufficient condition, because in one, okay, let me formulate this first, then I will discuss other one. So the condition that omega is a delta covering net for Rm is sufficient with a small enough delta for the inequality holds, and it's necessary with an additional condition that omega is delta 1 and packing net. Theorem 3, it's about Q equals to infinity, L infinity discretization theorem. So let omega be a delta covering net with a small enough delta. Then for any f from BV, the following inequality holds. And part B, also necessary condition, which almost coincide with the sufficient one. Let the above inequality with a fixed number C3 be valid for any function f from BV. Then they exist such delta that omega is delta covering net for Rm. So the condition that omega is a delta covering net for Rm is necessary for inequality holds, and it's sufficient but for small enough delta. This small enough delta, it's the only difference between sufficient and necessary conditions. In the univariate case, a precise criterion was found by Berling, and his necessary and sufficient condition, not simple. It has something to do with the density of knots. And at least I don't see how to extend it to a multivariate case. Simplified versions of discretization theorems presented below immediately follow from theorem 1 through 3. The following corollary holds. If x nu is delta 1 packing and delta covering net for Rm with a small enough delta, then the following typical LQ discretization theorem, L infinity to discretization theorem holds. For Q equals to infinity, we can specify that it's in part B. For any gamma, there exists delta such that if x nu is delta covering net, then this inequality poles. The proofs of theorems 1 through 3 are based on certain geometric results, properties of algebraic polynomials, and an approximation of EFETs by polynomials and other EFETs. Major ingredients of proofs of many discretization theorems are based on Markov-Bernstein-Nikolsky inequalities. We need them as well, and some Bernstein type inequalities are used, of course. The proofs of discretization inequalities from part A are essentially based on the following Sobolev type estimate of the modulus of continuity of d-differentiable functions f on a cube. This type of inequality, actually, it's not difficult to prove by using Sobolev type estimates. Statement A of theorem 1 actually follows from this Sobolev type estimate and some combinatorial geometry results. The proof of statement A of theorem 2 is more complicated because the premises of the statement do not include the assumption of f from LQ that prevents us from using Bernstein type inequalities. That is why we approximate f by special EFETs Fn there from LQ now and prove statement A for those functions. Passing to the limit as n approaches infinity completes the proof of statement A. The idea of using functions Fn actually belongs to Logvinenko, who applied these functions to the proof of inversion of theorem 3a in case of q equals to infinity. However, we use different techniques for constructing and studying those functions, which allow us to extend Logvinenko's result and some discretization theorems to q between 1 and infinity. Note that construction and properties of Fn are based on approximation estimates of functions f from BV by multivariate algebraic polynomials. These estimates extend and or strengthen earlier results by Bernstein, Logvinenko, and the speaker. Okay, so the proofs of parts B are based on some properties of delta 1 unpacking and delta covering nets. And now we move to discretization theorems on a cube. So we are done with discretization theorems on the Euclidean space. The discretization problems on compact sets is unexplored for general entire functions of exponential type. Certainly, there are several results, many results for trigonometric polynomials, for exponential polynomials, but proving certain estimates for general functions of exponential type is a kind of not easy problem. Next, we discuss a couple of theorems for which describe L-infinity discretization results for entire functions of high exponential type on the cube QBM. The conditions for the next theorem look very specialized, but they are helpful for application at least to exponential polynomials. To formulate the corresponding result, we need the function, which was introduced by Bernstein in 1947. This function has unique positive 0, tau 0. And the following theorem holds. Let f be entire function that satisfies this condition. So from here we see that this is a function of exponential type sigma in each variable, where sigma is defined by that. Here m, b, tau are fixed, and n could be very large. And the constant dn in front of this inequality is a constant that satisfies the second red condition. This is the first red condition, the second red condition. So if these two red conditions are satisfied, then the regular L infinity theorem holds. So in other words, for any gamma, there exists finite set like that, with a number of elements less than or equal c times n to the power m, and this inequality holds for every function f satisfying the two red conditions above. It's easy to verify the red condition of theorem 4 for the following class of entire functions of exponential type. This is example. Let f be an entire function in one variable satisfying this inequality, and in addition we assume that f0 is positive on Rm, then any function of this form with this kernel where sigma is positive and mu is a positive measure on the cube, then this function is entire, and moreover this inequality holds. So it's kind of easy to verify the red conditions of theorem 4. So in other words, the set of all exponential polynomials of this form with non-negative coefficients is a subset of the family of all functions from example 1 for this f0. And all positive discrete measures mu on Q. Therefore, theorem 4 holds true for this set of exponential polynomials by example 1. And from here, we have that discretization theorem for this set is possible. For exponential polynomials with any real or complex coefficients, the problem of verifying the red conditions of theorem 4 is more complicated, but we have nevertheless one L infinity discretization theorem for certain exponential polynomials with complex coefficients. The next theorem holds. Let B be independent of given number n. In addition, let this is an exponential polynomial, kind of exponential polynomial of degree at most n in each variable, okay? Then for any gamma, there exists constant c, an integer n0, and a finite set with this estimate for number of elements in the set such that this inequality holds. So regular L infinity discretization theorem holds for every exponential polynomial En. And this estimate of theorem 5 is sharp with respect to n. I have 40 seconds to complete. To prove theorem 4, we approximate function f by algebraic polynomials of degree n in each variable. And this step reduces discretization theorem of theorem 4 to discretization inequality of the theorem by Day and Primock we discussed before that, okay? So, and theorem 5 also can be proved by using theorem 4. It's actually corollary of theorem 4. And I would like to complete my presentation by thanking you for your patience.
Yeah, same. Are there any questions? Please.
I have a question out of curiosity about your gap between necessary and sufficient conditions in theorems 2 and 3. So what do you know, or what do you think? Is it essential that you need some additional conditions?
You need in theorem 3?
Yeah,
Oh, okay.
theorem 2 also, in theorem 2.
Oh, in theorem 2.
So do you think you need it really, or is it just that your proof is such that it doesn't work? Do you know, what is your conjecture?
I don't know. First I thought that actually it should be necessary and sufficient condition. I just cannot prove it. I spent a while trying to prove it and I could not. Maybe then I learned about the result of Berling, who proved the necessary and sufficient condition. No, it was not easy. The condition looks not easy. So I don't think that just being delta cover net is sufficient, is necessary too. So I cannot tell you. I cannot tell you for Q between 1 and infinity and for infinity as well. No, I'm sorry. I think maybe I just cannot do that. Maybe. But I doubt that this is necessary and sufficient.
But in your theorem too, it's, your packing condition looks strange because it's more points. So for sure, it's not necessary. If you take more points, it will be better, always better. To have a estimate discrete norm from below by continuous norm.
If you put more points into each cube,
into your set of discrete set. So it's covering
okay,
it's necessary,
so,
of course, something like this. But
this is no. If you put more points, the theorem 1 is okay.
no, theorem 2 I meant.
Oh, you're talking about theorem 2?
Yeah.
So why I put you mean delta n condition
your
into
statement there is a requirement.
Yes, necessary. No, statement is sufficient, just delta covering it. Okay.
No, there is a packing condition also.
Okay, necessary. Yeah.
It looks strange to my mind because more points, better estimate.
But if more points, so the left-hand side could be
bigger.
So if you have, okay, I think I need to think about that. Thank you.
Are there any questions, comments? If no, let us say thank you again.